if and only if Q, well, with letters this way, or if you're using arrows, you know, implication, but it's both ways. An if and only if, an if is a two-way statement. It says if P is true, then Q is true. And it also says if Q is true, then P is true. It goes both ways. Right? So to prove an if type statement, an if and only if type statement, you have to prove it in two directions. In other words, it's a two-part proof. There are two proofs. You have to prove if P then Q, and you also have to prove if Q then P. Okay? So to prove this corollary statement or theorem statement, we have to do two proofs. Now, Sipser is, my guess he's not a professional pure mathematician, I don't know, but he does not follow the fairly strict, strongly conventional, let's say, customs of the pure mathematicians. Now, since one of my aims is to try to educate a whole generation around the planet of mathematical physicists, so that you know, if you keep following me to high levels, that you will be equally at home in language of pure math as you are in math physics and some computing. Okay. Now, so I suggest that you start learning from early in your education, if you follow me right through, to follow the pure math conventions. And pure mathematicians, they get annoyed when somebody starts doing a if and only if proof, when they start with the only if part. Right? The convention is you start with the if part, so you're not figuring out. Oh, it's just confusing. If you're, as a pure mathematician, you're highly accustomed, for years, let's say, starting with the if part of this two-part proof, the if and the only if part. So if somebody else starts with the only if part, it's confusing. So I suggest you conform with the custom of the pure mathematicians. After all, they're the guys who dictate, in a sense, these mathematical techniques. They are the mathematicians, right? Okay. So the pure math custom is start with the if part, and then later we'll do the only if part, right? So let's talk a little in general about the if statement. Now, if you have followed my first course in deGarisMPC, the first course that I did on finite group theory, we did lots of if and only if type proofs, because it was a pure math course. So after a while we just routinely started with the if part. So it was just taken for granted that was the convention. Okay, so here let's do the same. So we start with the if part. Now don't worry about what these words mean. Just think of this as a mathematical statement. P, if and only if Q, and that's P and that's Q. So the if part, that's the same thing as saying P if Q, right? And the only if part, that's the same thing as saying P only if Q, right? So P if Q, what does that mean? Now think with words and logic. P if Q, how do you interpret that? In other words, P is true if Q is true. So in other words, if you have Q, then you know P is true. Right? Q if true. So Q if P. Oh, sorry. P if Q. P is true if Q is true. Alright, so that means if you do have Q, then you know P is true. So using an if-then type statement, if Q then P. Right? So if Q then P. So the if, you can write this way. So for the if part, it's if Q then P. In other words, whatever's on the right hand side you start with, and then prove what's on the left hand side. So you start with Q and you have to then you have to prove P, right? So you start with this and then prove that. That's the if part, right? The if part is if Q then P. If the right hand side then the left hand side. Okay? Alright, and the other way, the only if, so P only if Q. Well, think about that. What does that mean? P is true only if Q is true. So there's only one way you can get P, and that's via Q being true. So if you do have P, Q must have been true, because that's the only way you can get P. You know, P only if Q, only if Q. Right? So if you do have P, you must have had Q. So only if you can rewrite as if P then Q, which is the opposite of this one. So in other words, you start with the left-hand side and get the right-hand side. So you start with if P then Q. So you start with that, and you have to prove that. Right? So the if, start with the right-hand side and prove the left-hand side. So in other words, if Q then P. And the only if part, the second part, you start with the left-hand side and prove the right-hand side. Or in other words, if P then Q. Okay? Memorize those. Very useful. Now, I spelled this out many times in the first course, if you followed it. But some of you computer science not so interested in math or physics, you're just doing this computer course because it's a computer course. Okay? So this might be new to you. So memorize it. It's important. Right? If and only if proofs, take this form. All right. Now let's actually do it. Right? Now let's actually prove if Q then P, and prove if P then Q. Okay? And if we do both, if we can prove both, then we have proved P if and only if Q. Okay? Well, let's do it. So here's the proof of the if part, the if half, if you like. Now, typically in an if and only if proof, one of them, maybe the if or the only if, one of those two will be harder to prove than the other. Okay? That's often the case. Expect that. It's improbable that they'll be equally easy or equally difficult. That's less probable than they'll differ in their level of difficulty in the proof. That's sort of more common sense. All right. Well, okay. So let's do the if part. Now the if part says if Q then P. In other words, start with the right-hand side and prove the left-hand side. Start with the right-hand side. Here's your statement Q. That's with your P. So we start with this. We assume that's true. We assume Q is true, and therefore we have to prove that P is true. So let's do that. Okay, so some NFA recognizes it refers to the language. Okay, so there's an NFA that recognizes the language. Okay, now if an NFA recognizes the language, there is an equivalent DFA that recognizes the language, right? Because Theorem 1.39 says that for any NFA there's an equivalent DFA, right? And Q says there is an NFA that recognizes the language. Well, if there's an NFA that recognizes the language, there is a DFA that recognizes the language, because that's what equivalence means, right? They recognize the same language. And therefore, there is a DFA that recognizes the language. And by definition, if there is a DFA that recognizes a language, that language, by definition, is regular. Okay? That's P. So we've proved P. So if Q, then P. So we've proved that. Right, now the other half, the only if. So only if means if P then Q. In other words, you start with the left-hand side and you conclude, you deduce, you prove, with mathematical logic, you prove that Q is true. Right? So we start now with this and we have to prove that. Okay, a language is regular. Okay, so we start with that. A language is regular. We've got a regular language, and we can conclude from that that language has some automaton, finite automaton, that recognizes it. Okay. Now, for any well, it goes both ways. Yeah, I haven't spelled that out actually, have we? We've gone from an NFA to a DFA, but how about the other way? Haven't spelled that out, have we? Actually, okay, that's a bit of a question mark. All right. Okay, so we're given this. So the language is regular, therefore there is a DFA that recognizes it. And I'm assuming that because there's a DFA recognizing it, therefore, since there's a DFA and an NFA that are equivalent, strictly we haven't shown that, have we? We've only shown that if there's an NFA, there's a DFA. But how about the other way? Question mark. Right. Okay, so there is a DFA that recognizes this language, and assuming therefore that there's an equivalent NFA also recognizes it. Okay, and that's Q. I have a bit of a question mark there whether the equivalence between NFA and a DFA is in both directions. And we've only, this only proves it one way. Right? It proves it from NFA to the DFA. Is the other way, is that obvious? Like, you could argue a DFA is just a special case of an NFA, right? I guess that's what's been used here in this proof. All right. Okay, so we've proved it, well, with that question mark. We've proved it both ways, right? So P if and only if Q. In other words, here's your P, this is your Q. Now what we do next, we do an example. You'll be given a concrete NFA. Fairly simple, just a three-state machine, but it's definitely an NFA because, well, on two counts there's an eta arrow and there's also two exit arrows, two transition arrows that both have the same input symbol coming from the same state, the same node. Okay? So it's definitely an NFA, and we will spend the next almost 2 sessions on it, analysing it, finding its equivalent DFA. Okay, so till next session.